Okie dokie, science time. Let's, please don't touch that. Good. Okay, don't touch it. Don't touch it. Don't touch it. What we're talking about here, viewers, Josie, is this keyboard that these kids are fighting over that they're not supposed to be touching, but they keep touching it on purpose. Okay, today we're talking about systems, and system models. So please write that down. The objective was describe natural and engineered systems and identify the role of system models. So let's write that down as well. Do you guys see how the... my spray is gone. I don't know. I'm just going to do it like this. It's not going to look great. Sorry. Should I spit on it? I don't even know. Ooh, that looks really bad. Hey, Cody, pop up and go in. On the front table in the lab is a little, like, plastic tote, and it has the spray bottle in it. Would you grab that, please? But don't hurry or anything, okay? Just make sure you go really slow about it. We are going to write the objective down. Do you see how the objective is linked to the title? Describe natural and engineered systems and identify the role of system models. Thank you. Thank you. Sorry for hassling you on your way in there. It was kind of slow, though. Okay. Now that I can erase this, we're going to write that objective down. And I would like it if you would write it down, too. Describe. I mean, I'm going to take my time to write it, so you might as well take yours to write it, too. Describe natural and engineered systems and identify the role of system models. Hey, what does this remind you of? The things we're talking about right now, do they remind you of anything that we talked about earlier in the school year? Hopefully. Hopefully, Garrett. Yep. Okay, what, though? Say it. Yeah, what are those? You're pointing the right spot, so you are right, just to say their names. Someone can help him. No, which one? Yeah, CCC, what's that stand for? Thank you. Yep, good. Cross-cutting concepts. Everyone kind of, on average, we all kind of got it right. Cross-cutting concepts. One of the cross-cutting concepts of science is systems. Yeah, and yep, that's right. Systems and system models. So we're talking about, in fact, we were talking about the exact words that were that CCC. So this applies to all science, and it applies to all engineering. What we have over here is that we're going to talk about natural systems, which apply to science, and engineered systems, which apply to engineering. Give me an example of a system. We had some in the bell work, so let's have one example of a system. Any system, you. Respiratory system. Okay, so we're going to choose this. First of all, is this a natural or an engineered system? And what I mean is, yeah, it's a natural system in that human beings did not engineer it. That's what engineered system means. We're not going to get into theological, religious arguments. That's not the place for this. We're talking about engineered system specifically means human beings and engineered it. And we know that didn't happen for this. So the respiratory system is a natural system. Okay, there's another one. The subway system of, we'll say, of Moscow. The subway system of Moscow. We want to be specific with that. For this one, we should say of a human. I just assume that's what you're talking about, Miranda. A lot of other organisms have respiratory systems, but I assumed you were talking about the human respiratory system, because that's the one you probably know the most about. And this was an engineered system. And we kind of have this, I wouldn't say instinctual, but a pretty, just based on the knowledge we already have, we have an idea of the difference between natural systems, those found in nature, and an engineered system, those that are designed by human beings. Similarities. What are similar about these two things? Okay, yeah, that doesn't count though. Be more specific. Let's think about JJ's bell work, the definition of system. Okay.
They both have a specific purpose.
Yeah, that's function. They both have a specific job,
And
function.
They can't really join with us, like the subway stuck on the tracks.
Okay, they are enclosed.
Yeah.
They're enclosed. That's good. I'm glad you pointed that one out. I didn't think you'd get that one. What else? What makes them a system? Why are they not just like...
They run, they move, they do...
Yeah, okay, yeah. It takes more than one thing to work. Greater than, not greater than or equal to, greater than one thing. And I'm going to put that in quotes. Why is a block of cheese not a system? I mean, on some scale it is. So We'll talk about that in a second, maybe. But why is thinking about just a block of cheese? Why is that not usually considered a system on the macroscopic scale? It's just one thing. It's not things working together. And I'm going to put working in quotes here. Working together. Why do you think I put working in quotes? No, I put it in quotes though. Why? You're kind of right, but
Because they don't work.
yeah, they're not. We talked about this just barely when we talked about the CCCs in general, but the things don't have to have agency. Sometimes they do, and what I mean is they don't have to be able to think for themselves and operate on their own. And when we use the word work, it kind of implies that they do. Like the school as a system is human beings working together. Like actually, this word would be not in quotes in that case. We are actually working together. We have agency. We're choosing to do things, and we're choosing to work together. That's what the school is as a system. But your respiratory system, it's not like Osmosis Jones, a movie that was from when I was a child and when you guys were negative 6 years old. You guys were dead back then. But it's not like that, where the cells are like, hey, you want to get some oxygen? The other cell's like, yeah, let's get some oxygen. They don't talk to each other. They don't work together in that way. They function together. So that's probably a better word. They function together. And there's some result of their functioning together. And it's not like it's their goal. It's not like, oh, in quarter 4 of 2013, we really made a lot of oxygen for that guy. That's not really how it works. There's no goal necessarily, but there is a result at the end. Okay? So let's talk about, and these things, here's the next thing. These things are called, what does your book say they're called? Or what does your exploration say they're called? Which is a much better word than things.
Resources.
No.
Systems.
Look at it, maybe. Well, it's a vocab word, so I wish you did. It was in bright orange. Miranda's going to find it.
Oh, it was, yes.
Components. So that's another thing they have in common. These both have components. What are some components? We're not going to list them all. What are some components of the respiratory system? Lungs, tubes? Let's not call it that.
Or intestines. No? Oh,
Okay,
respiratory.
valves. That's
Yeah,
okay.
I thought we were talking about intestines.
Okay, I'm just going to go on. Bronchioles.
Esophagus.
No, trachea is what you're thinking of, etc.
Oh, the bronchial.
Okay, what are some, hush. What are some components? What are some components of the subway? Okay, there's probably, we'll call it an engine. Wheels.
Those are called tracks.
Tracks.
Yeah.
Rails.
No,
Okay.
Electricity. The tracks have to go on the rails though. Like the wheels that have the tracks.
Etc. ETC stands for etc., which is Latin for and all the rest. Meaning that there's more stuff, we're just not going to list everything. Components. And a system also has inputs and outputs. This is an easy one. What are the inputs? Okay, let's define input real quick. You should already know what this is, but what's an input? Something that goes in. Yeah. So an input, what's an input of the respiratory system? In human beings. Air. All of the air. The air mixed together. Mostly nitrogen, some oxygen, some quite a little bit of some other stuff. What is the output of the? There are two I can think of. Okay, as a waste product, CO2, and as the point of it is what? Oxygenated blood. Yeah, oxygenated blood. Okay, what about the subway system? What's an input? What's the point? Humans at point A. And what's the output? Yeah, the same humans now at point B. What's the waste product here? Sure, we'll put smoke. Some kind of pollutant, I'm sure. Some kind of pollutant. There's other things. Et cetera, means there are other things.
No, because subways are, they're electronically controlled by the trails. Like if you step on a subway rail while it's going, you get zapped.
Yeah, but there's still, power had to be made somewhere.
Yeah.
Pollution. Smoke. You're right. Smoke is it is definitely a misnomer here. I don't think for a long time subways have actually run on diesel or coal power like actual locomotives do because it's an enclosed area. They are always, as far as I know, like JJ says, electric. But there is probably some kind of pollution from the subway. I'm sure there is.
Even the electronics.
What do we call? Okay. Trash. Perfect.
Dirty human.
Yeah, dirty humans. Yeah, nice. In both ways. They're actually covered in filth and they have a dirty mind, so that's perfect. And this is implying that it's making them be that way by being on the subway, which I think is cute. Anyway, what do we call the relationship between the inputs and the outputs, or even the inputs in each other, or the components? The relationship between components is called a what? Yeah, I don't want to. A relationship between components is a what? No, not always. What is the lungs are whatting the air. They're something with the air. No. The human beings are something with the engine or the tracks or whatever. They are. There's a more broad term I'm looking for. What? Say it again, Miranda. Yes, interacting. The relationship. I don't know why you guys think you have to talk all the time. I do value your input, but I want you to raise your hand or something first instead of just talking all the time. The relationship between the components are their interactions. They are interacting. I'm going to change that to interactions.
That's what I think.
Yeah, interactions is better. Your book has a great example. I'm just going to call it the book because that's what I'm used to saying. The book has a great example of the interaction between an elk population and a wolf population that you saw. Did you do that one? And that was a mathematical relationship. So sometimes these interactions and these relationships, sometimes they can involve math. In fact, in science, they usually do involve math. Could we do some math about the size of a person's lungs and the amount of air they can breathe in? Sure. Absolutely we could. And so that would be a way of measuring the interactions and the relationships between them. Questions about systems in general? I appreciate your input. I really do. I want you to try to rein it in a little bit. I don't even mind if some of your inputs are jokes, but let's try to simmer down just a touch. Next thing we're going to talk about is system models. Okay, so write that down. That's the next bit. System models. What did you just say, Lucas? Did you say you didn't write any of this down? Hey, what happens if you didn't write any of this down like some people didn't? No, maybe. But what? Do you have a second, like is there a plan B? You can go watch the video. And in fact, what if, this is probably true of someone who's just keeping themselves hidden, what if I just erase something you were currently writing? What can you do? Watch the video. You can watch the video. That's why I video this. System models. What's a model, Cody? All right, fine. Not always. I was hoping you would say, no, never mind. I asked Cody specifically because I thought he would say like sexy lady doing like modeling some clothes. Both of those are related though. Both of those are, I'm going to call it this, idealized representations. What does a model do? Like what's the job of a human being who is a model? What is their job to do? Yeah, to advertise. They're trying to show you, they're trying to imply, not they, but the people for whom they work are trying to imply, if you buy this iPhone or these clothes or this purse, you will look like this, right? So that's an idealized representation. You won't, and guess what? You look better than that person probably, so don't try to have low self-esteem. But it's an idealized representation. It's what you could look like ideally. Maybe, I don't even know if that maybe sound like I'm implying that you don't. They chose this person to represent their product ideally, and what their mind is ideal. And I'm not saying that's perfect, and I'm not saying that's how a human being should ideally look, but that's how the designers made that. Does that make sense? Yes. But it's also, when we think about natural and engineered system, it's an idealized representation with shortcomings. It always has shortcomings. What are the shortcomings? No, I don't mean personally, but what are the shortcomings of the model who's modeling those clothes in that example? What's the drawback? What did you say, Lucas? Yeah, exactly. The people are different. It's not going to look the same on you or on another person as it does on that model. That's a shortcoming. That's a shortcoming. What are the shortcomings of the kind of models we work with in science? Well, we know there are shortcomings, and that's the point, is that there are shortcomings. It varies per model. But look at this. Okay, great. It's the solar system. Is this a model of the solar system? Yes. Is it an idealized representation? Yes. Does it look Like the actual solar system? No. Why? What are some problems with it?
Because it's not 3D. The sun doesn't look like it. It's
Not 3D. Okay, what else?
It's not colored.
Okay, so far there are only 4 planets. What else?
There's not colors.
Okay, they aren't. There is a color, but they aren't it's not the correct color. What was yours? What'd you say, Brinley? Not the right colors. Yes. What else? The sun don't look quite right.
There's no specific order.
Okay, these things don't actually. They're probably not in this exact position in real life right now, Tommy. Okay. Do these actually exist? Does this line exist? Okay, no, that doesn't even exist at all. Luke, okay, yeah, that's the main thing I was getting at here. They're not to scale. There are lots of shortcomings, but, and I don't mean ideal in a way that this is perfect. That's not the same thing. Let's put that. This does not mean perfect. But is this an idealized, meaning it's an idea? Does this represent an idea of the solar system? Yeah. Can I use this to educate people? Is this model useful? No. So yeah, even though it has shortcomings, we recognize it's still useful. What could I show maybe someone in this class, but definitely like a second grader, about the solar system from this? Okay, the sun is in the middle. I could show them that. What else could I show them about it? Okay, the planets orbit around it. What else could I show them about it? Well, I could show them the order. This is Mercury. This is supposed to be Venus. This is our home. And this is Mars. And that's true. That is the order of the planets in order away from the sun. So there are true things about this model that I can show people, even though the model is imperfect. The model has shortcomings. I could say that the sun is bigger than all of them.
And you could show them that the moon isn't a planet.
I could show them the moon lives over here next to Earth, and it is not a planet. So models have uses. They're idealized representations, but they always have shortcomings. And we recognize the shortcomings, but they're still useful. Would this be useful to show the scale of the solar system? No. There are models that do show the scale of the solar system, and those have a different purpose. This one could show the relative positions, the size of the sun, and that they orbit. And that's good. That's what we would use this model for. Why would I use this instead of just why don't I just take the real solar system and show it to second graders?
Because
It's too big. It's too dang big. And so models, not only are models idealized representations, but we have to use models to understand some subjects. Hey, how about I just get one of the atoms out of my laptop here and show it to the second graders to show them how an atom works? This is a real atom right here. Can I show them how it works? No, it's too small. So I need to use model. I have to use a model to show students. I have to show students, even though this is literally made of atoms, I have to use a model to show students how an atom works because they're too small to see. The solar system is too big to fully understand on its own scale, so we have to draw models or use models. Models are idealized representations with shortcomings, and we know they have shortcomings. No one's like, now listen, this is not a solar system. I know it's not a solar system. It's a shortcoming, but we work around those because models are still useful. Is a model like a simulation, kind of? Yeah. What's different about simulation, would you say?
Simulation is kind of like in real time.
Yeah, it's a simulation, I would say, is supposed to function based on the same inputs as the real system. It'll have the same outputs. So it simulates the real system still with shortcomings. It's a kind of model, but it's supposed to have the same function as a system. Do you have questions about system models and how they're used? Do you see that they're useful even though they have shortcomings? And just like the lady who's a model, she has shortcomings too, but she's still a representation of what she's trying to show. She or he. Models can be hymns too. You go for it, Lucas. You don't let your dreams be dreams. Does anyone have questions? Do you understand systems a little better from our discussion?
Yes.
Does you understand system models a little better?
Yes.
Do you feel like you had input in the discussion?
Yes.
Did we describe natural and engineered systems and identify the role of system models?
Yes.